I'd like to welcome everybody to the April 2026 DAS meeting. First item on the agenda, do we have any people who are new members or guests or people just checking us out who'd like to introduce yourselves? Yeah, that'd be great.
Oh, okay. Hi. Hello. Hi. My name is Ron. I was actually working here and Dave invited me. I'm a retro computer enthusiast and a ham radio enthusiast. Not really too much into astrology yet.
Oh, thank goodness. We're not either.
Not yet. Not yet.
Astronomy.
But yeah, I'm here to get some information.
Awesome.
Yeah, keep my interest.
Welcome. And thank you for making it a better observatory for us.
Yeah, that's awesome.
Sir?
Hi, I'm Dilip Patel. I just joined a few months ago. This is my first time here.
Great, welcome.
Tom, I'm Tom Skrovanik. I joined a couple weeks ago, 3 weeks ago. I went to the first start party. Messed around with this 55 years ago, and then life started happening. A couple years ago, I started acquiring hardware and learning from YouTube and from everybody.
Great, welcome.
Thank you.
I was over at the,
Tuckahoe.
yeah, in Tuckahoe and Brandywine Creek Park, already, so he's jumped right in as volunteers. Thank you, Tom.
Very nice.
Anybody else?
Anybody else?
Hi, Lisa Hall, new member.
Welcome.
I'm here to learn.
Welcome. For any of the new folks, everybody's friendly. Well, almost everybody. After the meeting, hang out, ask questions. Probably can get you you're going to be doing a tour. So please hang out. We have refreshments after the meeting. If you're a member or not, it really doesn't matter. Actually, a great point to all the DAS events are open to members and the general public alike. So while we certainly like and encourage membership, it's not strictly required. Come to any event that strikes your interest. But yeah, certainly come and hang out after the meeting and let us get to know you a little better.
But it should be noted there's great benefits to membership.
Yeah.
But we'll get to that later. All right, real quick, I'm going to share the screen. I'm going to put up Sydney's presentation. Sydney unfortunately could not join us this evening, but he's got a cool thing here. Here, let me click pin and I'll minimize that so it's out of the way. All right. So very important point is this spring we have our 2026 DS board members elections. So as per our bylaws, tonight is the last night where you can join up and run for one of the officers' positions. So we got president, vice president, secretary, and treasurer. So if you'd like to nominate someone or yourself for any of these positions, you could send an email today to sidastronomy@yahoo.com or give your name to me and I'll give it to Sydney. Tonight's meeting. Please note that the current people, what's up?
Nothing.
Okay. Please note that the current people who are running for these positions, our secretary is Bill McKibben and he's running again. Our treasurer is Bob Treblecock and he's running again. Our vice president is Jeff Lawrence and he is running again. And myself, Robert Lancaster, and I am running again. Currently, I don't think anybody else is running for any of those positions. But if you would like to, you certainly can. We would encourage you to sign up, run for one of the positions. And if you want to know more details about the election or about any of the candidates for the various positions, you can check the Focus this month, where there's a nice article about each one of them written in their own hands. Wonderful. Let me close that real quick.
And voting for members is one of the actual benefits of membership. So,
yep. Next item, we have outreach events coming up. Very busy at the moment. You want to tell us about that, Greg?
Yeah, it's been, we're getting into a busy period here. I kind of coordinate with a couple of the state parks for the public outreach. I've been doing that for a long time, even though Jim Kirshen is the main coordinator for all the other things, and I'm work under his authority, those two parks. We were over at Brandywine Creek last week. Coming up this Friday, we have an event scheduled at Bellevue State Park. These events are scheduled 4 to 6 months in advance with the state parks because it fits in among their other activities. So it turned out that things kind of got jammed up this week. It's a busy week. But Friday is looking a little iffy anyway. I got a couple of on standby volunteers for Friday, even though it doesn't look like we're going to do it. And then the Creamery is coming up for the first time
Yep.
on Saturday.
Our first event at Woodside Creamery will be this Saturday. Please note, everybody, we have done a shift just to keep everybody on their toes. We typically have done them on Friday nights, but for reasons I'm not going to tell, we're going to do them on Saturday nights this go around. So our first event is this Saturday, April 25th, starting at 11 a.m. No, 7 p.m. 7 p.m. And again, I haven't even looked at the weather yet, but keep an eye on the groups.io and the weather. I tend to be, what's the word, less particular with Woodside because, as I say, even when it's cloudy, the ice cream is still good. So we tend to hold that unless it's actually raining.
Unless it's actually downpouring.
Yeah,
The public still gets a kick out of looking at telescopes.
yeah.
So it's a show and tell Q&A kind of event and still.
And good point. We always say outreach is a great way to get started in the hobby. If you think you do not know enough, you're wrong. And if you don't have a telescope, that's not a problem either. There's two options: come anyhow and answer questions, or even better, as a DS member, we can send you home tonight with one of our loaner scopes that you could use at either of these upcoming outreach events. So outreach is a heck of a lot of fun. I enjoy it. So let's hope for some good weather this weekend.
So things got kind of jammed up here, but I think we'll spread out a little more in the upcoming months. The other thing that's happening is tonight and tomorrow morning, the Lyrid meteor shower peaks. So it's very easy to find the radiant. It's very close to bright Vega. Vega will transit around 4 a.m. So it'll be at its highest around 4 a.m. Meteor watching is always better after midnight when that source gets higher up and you get, early on, you only get half of the meteors because the others are going beneath the earth. We see the ones coming on our side. Later on, closer to dawn, you get the whole show coming from all directions.
And the moon will be down.
Sorry?
And the moon will be down.
And the moon will be out of the way. So it's a good opportunity. Weather will cross our fingers. 5 o'clock is when it will be the highest, but that's starting to show some twilight by then. So midnight to 4 is probably the best opportunity for this one.
Very good. Thank you very much, Greg. Next item, the APC, Bill.
Yes, the next meeting of the Astrophotography Special Interest Group will be this coming Saturday at 1 p.m. On Zoom. And an announcement will go out over groups.io email list.
Okay. Very good. Thank you. And next thing, Mary, are you there?
Yes, I am. Yes, I am.
All right, you want to tell us about the book club?
Yes, good evening, everyone. The book club will be meeting on Sunday, not our typical Thursday meeting, on Sunday, April the 26th at 4 p.m. in the afternoon. Our schedule was changed to accommodate our author, Emma Chapman, who will be joining us from Nottingham, England, where she is a professor at the University of Cosmology. We will be discussing her wonderful book, First Light, Switching on Stars at the Dawn of Time. Emma will speak about her book, and then we will have a discussion between Emma and another professor of cosmology at the University of Delaware Olga Navros. The meeting will be led by our book club member, Greg McNiff, who's a wonderful meeting leader and dedicated to reading and astronomy. So I hope you will all be able to join us. Your guests are also welcome, very welcome. The meeting has been picked up by the Astronomical League. So we've had many inquiries from people from Muncie, Indiana to Vermont, who will be popping in to listen to what Emma has to say about the book. So thank you. Have a good evening.
Thank you very much. Wonderful. Are there any other announcements? Yes.
I hope I'm not, I don't know if anybody is going to talk about it, but just a reminder, tomorrow night at the University of Delaware at Clayton Hall,
Oh, right.
we have the Vernon Lecture. So it's going to be called The Search for Earth 2.0. And Dr. Jesse Christensen is going to give that talk. Oh, we have plenty of printouts here, so be sure to take one. But make sure you register online. I think Kim Green sent out some literature about that, so you can register online. It's free, open to the public, right down at Clayton Hall, University of Delaware. So I think it's going to be fun.
Those Vernon lecture talks have been nothing but spectacular. So
If you want to see more, here's the flyer. There's multiple copies of it out there in the hall.
I'm sure lots of us will be there.
Yep.
Yes, I definitely will be there.
Likewise.
It's gonna be a great time.
I actually have a date. Liz is going to join me.
There you go. There you go. All right, any other announcements? Yes.
Brief one, sorry.
Yep, no problem. You're good. No problem.
Friday Night Lights is June 26th. Some of you have been there before. We bring our telescopes and there'll be two bands there. It's on the Cheslin Preserve, sponsored by the Natural Lands Trust. I'll be getting an email out eventually from groups.io with all the details. We're allowed to bring 2 guests this year, and it's from 7 to 10. Unfortunately, the event ends before astronomical twilight, but we're going to have the moon out, so we'll be able to do some good entertaining with our scopes and the moon.
All right. Very good then. Any other announcements? All right, I think that's it then. Jeff,
all right.
next up.
So for our main topic, we are rejoined by longtime friend of the DAS, Rob Cordivari. Rob's been a long-standing member of our Friends to the North. I don't mean the Canadians, I mean the Chesmont Club. And more closer to home, Rob was the esteemed recipient of the DAS's Luther Porter Award in 2014, if I remember correctly. Again, a great segue from the outreach conversation. Part of what contributed to him earning that award is Rob initiated an event called, is it Starfest?
Starfest.
Which, I mean, I don't know how many thousands of people have come through that event over the years.
So on the low numbers on any given year would be 400 to 500 would be
Yeah.
low. We had as many as 2,000.
Yeah.
Plus twice. So generally we got close to 700 or 800 people coming through during the course of the evening.
And you've done it 10 or 15 years?
We did it 26.
Yeah, thousands and thousands of people. So anyhow, with that, let me get myself set up here.
Yeah.
We'd like to welcome back.
CAS meeting.
Okay, Rob, all yours. And I'll be at the helm here for you.
Okay, you want me to do? Snap my finger.
There we go. Bark like a dog, and then I'll.
All right, thank you so much for having me come here. I really appreciate it. It's great to be back seeing everybody again. It's a great turnout, so it's really, really, really nice. I was asked, speaking of Starfest, I was asked to give this presentation by the people at Hopewell Furnace, which is where we have held Starfest for the past 10 or 12 years. I did not know at the time that they wanted this for the 250th anniversary of the birth of the country. They just asked me if I would do an astronomy program because they knew that I, was from Chesmont. So I talked to them. I said, yeah, I can do a program. what do you want it on? They said, oh, it doesn't matter, just whatever, you know. And a month passed, and then a few weeks more passed, and then finally it was getting close to the date. I said, well, what do you know, can you give me some specifics? And they said, well, how about colonial astronomy? Of which I really didn't know a lot about. So it was a really good opportunity for me to start researching it. And I found out a lot of really good information. It was kind of fascinating. So what I decided to do is I decided to look at astronomy now and astronomy back then and just kind of compare the two. And I thought I would just start out with some general astronomy just because it's kind of fun and it just gets us in the astronomical mood. And based on what I saw from, there's some new there tonight, you might find this information really helpful or just interesting. I would say if I might ask some questions about some general astronomy subjects. If you know the answer, flat out know the answer, then I'd ask you not to call it out. But if you don't know the answer, I might ask.
Then give the answer.
Then give the answer.
Right, okay.
I might ask you to take a guess at it and see what we think. So we can just go from there. Okay. So you are here, and this is our Milky Way galaxy. We are barred spiral galaxy, and contrary to what was originally thought, we are not in the center of anything. So we are in the outskirts here in one arm of the galaxy. So we are about, I guess, 30,000 light years from the center of the galaxy. And I would start out by asking those who don't know the answer, if they want to take a guess, as to about how many stars you might think are in our Milky Way galaxy. Anyone want to take a guess who doesn't know the answer, or do you all know the answer?
That number changed.
I don't know the answer, but I'm not guessing.
That number changed.
More than seven.
More than seven.
Yeah.
More than seven, and less than
Brilliant.
less than a trillion.
How
So
about 3 billion as a guess?
3 billion. Okay, yeah, that's a good guess. It's more like
3 billion and one.
right. It's more like 400 billion. So that'll just give you an idea of the size of the galaxies that we're talking about. So when you look in the sky and you see galaxies, like you can look up and see the Andromeda galaxy in the fall, naked eye, that's bigger than the Milky Way galaxy. So that has more than 400 billion stars in it. Now, those are estimates, but I like to use the higher estimate because it sounds cool. So, okay.
Monty Python said it was 100 billion.
What's that?
Monty Python said it was 100 billion.
Yeah, right.
But he was low because they upped the estimate.
Right. Okay. Okay. This could be a little tricky with the slot. We'll see how it goes.
Okay.
Okay. So, gravity rules in the universe. Everything is connected through gravity. So, we know that the moon goes around the Earth in how long? You can, anyone. Go ahead, you can scroll down. Okay, the Earth goes around the sun in a year. All right, how about the sun and the solar system going around the center of the Milky Way galaxy? You.
No.
I'm just teasing.
No idea.
Anybody want to take, okay, so go ahead.
200 million?
How much?
200 million?
Yeah, go ahead. Yeah.
Ah.
So that's a really good guess. That's a really good guess. Yeah. And then the Milky Way galaxy is moving on a collision course towards the Andromeda galaxy. Anyone want to know how long the two of those are going to merge?
That's a couple billion years, isn't it?
It's actually a little longer, 4.5 billion years before that happened. And interestingly enough, when that they call it collision, like you hear about colliding galaxies, like arc galaxies, they refer to them as colliding galaxies. But
they're really not colliding because there's so much space between the stars that they just kind of merge through and form new formations. But it's really amazing that they do not, there are no collisions in there. As a quick aside, if I was holding a basketball in my hand or a soccer ball and told you that it was the sun and asked you to tell me where the nearest star, if I gave you another basketball and said, where should we put this other basketball to be our nearest star, which is Alpha Centauri or Beta Centauri, Proxima Centauri, I meant, thank you. 4.5 million light years away. Where do you think I'd have to put that other basketball?
Miles.
Saturn?
How much? How far?
I was gonna say 20 miles. What, like, you mean on Earth scale?
Yes,
I would say about 20 miles away.
20 miles. Okay. Anyone want to go further or shorter?
At the moon.
Not that far. So one more guess. You said 20 miles.
700 miles.
700. So it would be like somewhere off the coast of California, like out, so, you know, kind of heading towards Hawaii. So, so here's one star here at Mount Cuba. Here's our nearest neighbor out in the Pacific Ocean, and there's 400 billion of those in our galaxy. That gives you an idea of the expanse. And what I like to mention to people is, you know, a lot of times people get hung up with how far away things are, like we're talking right now. But I also like to emphasize on how large things are. So imagine looking at the Andromeda galaxy, and you can see it naked eye. It's an incredible. It just boggles the mind to think that you can look up in the sky and see it. I mean, so okay. All right. So how about the speed of light? The speed of light is constant, it never changes, and it travels at what speed? I know a lot of you know this, so how about those who don't? You want to take a guess? One what? One. I can't argue with that.
See.
So it's 186,000 miles per second. Per second, not per hour, per second. So when I was talking about the Andromeda galaxy, I guess got a little bit ahead of myself because so when you're looking at that galaxy, it's 2.5 million light years away. So that means that the light that you're seeing when you look up and you see it has been traveling for 186,000 miles per second for 2.5 million years. So just think about how far away that is, but yet you can see it. So imagine how big it must be. So those two things kind of are related to one another. Okay. 186,000 miles per second. Okay.
What was the joke of that guy saying, or talking to God, and he said, what?
So since we just had this Artemis 2 moon launch, it's interesting, a good time to talk about this. I forget, so how many days did it take them to get to the moon? Like 3 or 4 days, is that roughly? All right, so at the speed of light, how long do you think it would take to get to the moon?
1 second.
Yeah, it's like 1.5 seconds. Next slide. Okay, and then to the sun? 8 minutes. Yep, very good. Okay, Alpha Centauri, we just talked about that, 4.4 light years. All right, here's one, since everyone has been like 3 for 3 here. The Hercules globular cluster, any guesses there? Open to anyone?
20,000?
25.
Good, yeah, 25, yeah, good. Yeah, 25,000 light years, yeah. And then to the Andromeda galaxy, you can go to the next slide. We talked about that. 2.5 million light years. So big distances, but you know, all these are in our Milky Way galaxy, except obviously for the Andromeda galaxy. So, okay. All right, so as a visual astronomer, the night sky means a lot to me. I know it does to everyone who's an amateur astronomer, but there can be a lot of astronomy done remotely, but there's something standing out under the stars with your telescope, looking at objects. Nothing can replace that. And I do think it's magical. And I know when I first got introduced to astronomy, it really changed me. It just redirected my whole process towards what I wanted to do after that first night out in the field looking through a telescope. I was sold hook, line, and sinker, and I haven't looked back one day since then. So I do believe that, you know, that it's very magical. And telescopes, I think, are the most incredible invention. I mean, I know there's a lot of great inventions, but the telescope is such a simple invention. It's so simple in its basic form, yet it's so amazing at what can be done. I didn't bring my props with me tonight, but so I have a 20-inch telescope. I'm sure a lot of you guys have 6, 8, 10, 12, 20. You have a 24-inch I just saw here. You can have, I've seen telescopes with so many wires hanging off of them. It looks like the back of my TV stand with everything. But when you, and I'm guilty of the same thing, but when you pare that all away, really what you're left is if you have a reflecting telescope, are two mirrors, a primary mirror and a secondary mirror. And if you have that primary mirror, let's go to the next slide and see if it's, yeah, okay. So let's go into this. This is my reflecting telescope, okay? And the way that it works is light comes, this would be great, thank you. So light comes down this tube and it bounces off of this mirror. And this mirror is curved to reflect the light back up to this mirror. And then this mirror reflects the light through the opening where you then put the eyepiece. In an ideal situation, which you couldn't do because you couldn't hold it steady enough, but if you could, someone could hold this 20-inch mirror on their lap, sit on the ground and hold it on their lap. And somebody else could hold this secondary mirror in their hand right here. And then somebody else could look where that light is reflecting and you'd be able to see the object that we're looking at. And that's it. That's a telescope. A mirror on the ground, reflecting to a mirror in the air, reflecting to an eyepiece sitting in the air, yet they're enclosed in tubes. That's how a reflecting telescope works. Okay? A refracting telescope is a little different. The light comes through an objective lens and then just gets refracted down to a diagonal mirror, which then reflects the light up to an eyepiece. You could also not have that and have the eyepiece right here. It would be very awkward. So this is more practical and the image gets righted when you do it this way, and it's easier for navigating around the sky. But again, this is just two pieces of glass, a lens here and a mirror here, and then that's your telescope. That's how it works. Okay. This one I do not have a Schmidt-Cassegrain. Anybody here have a Schmidt-Cassegrain? Okay, so you guys know how it works. It's a little different. The light comes through there's like a prism up here, and then it mirrors here, then reflect it back up to another mirror, and then down through the center of the tube instead of to the side of the tube like the reflecting telescope. So this just allows you to make a more compact telescope for the same size. So if you had a 10-inch, if you had a 10-inch reflector, it might sit, this high off of the ground. maybe it's depending on what the F ratio is, but just in general, 10-inch reflector might sit like this high off the ground. A 10-inch refractor would be feet long, and a 10-inch Schmidt-Cat is the smallest of the group because it maximizes its light path. So just 3 different kinds of telescopes. Okay. Interestingly enough, here's the James Webb Space Telescope, and it operates just like your the telescopes that we use as amateurs. Basically it's a reflecting telescope. The light comes in, reflects off of these mirrors to a secondary mirror, and then down through the center of the tube, and then instead of an eyepiece like you have in your telescopes here at Mount Cuba, instead of an eyepiece, you just have all your instrument devices here for studying the views. So still the very same basic concept. Okay. So this is just a quick list of the current space-based telescopes, and you can see there's a lot of them, and they operate in different wavelengths, and that's really the main reason that they're up in space, is because of the wavelength that they're operating in, and they have different orbits depending on what it is that they're studying. But if you go to the next slide, Jeff, this will give a better idea. So the reasons that we put telescopes in space are, first, you can get atmospheric turbulence. So the sky just, the atmosphere just is not steady. Even if you go to the steadiest parts of the world, there's still some unsteadiness there. And that can make images blur, and stars can twinkle. In space, that situation is resolved. Certain wavelengths are just blocked on Earth through the atmosphere, so that they definitely need to be space-based telescopes. As amateur astronomers, we can relate to this: poor weather, lost observing time; light pollution, objects look faint and dim and really disappointing. So all of that is corrected with space-based telescopes. This is an image. This is an interesting image. So this is a Hubble image. So this is more like an optical image, optical wavelength image. This is James Webb. So this would be infrared. And then this is a composite. So there's still a lot that they can do with the different telescopes to piece those together. Okay. Now these are the ground-based telescopes, and you can see some of these. The infrared, I think, is one that they can get on the ground. Radio you can do on the ground, and these are the different locations. So there's a lot of these also, and they're spread throughout the world. Okay. Now, the converse of why it's advantageous to have telescopes in space is why it's advantageous to have them on the ground. And so the atmosphere, you can still do visible light and radio through from the ground, and therefore you can make larger telescopes, obviously, on the ground than you can put into space. There are adaptive optics that can help with that twinkling of the stars. Ground-based telescopes are easier to just repair and to upgrade. And then some of this requires large arrays spread over miles. So, and I'll show you a picture of this in a second. And radio astronomy uses interferometry, combining signals from a lot of antennas to simulate the size, a telescope the size of a continent. And there's also a telescope to basically use Earth-sized telescope that uses telescopes from different locations all over the Earth. And they combine that together to create one image. Go ahead. So this is the Event Horizon Telescope, and you can see, and I'm gonna, okay, so you can see where these different telescopes are located, and they basically use them and combine the data, and basically you're making now a telescope that's as large as the Earth. And this telescope took the first picture of a black hole in the galaxy. It's called M87 in Virgo. And I did not get to put the picture of that into this presentation. I'll just hold it up on my phone so you can, hope you can see that. So this is the first ever image of a black hole. And it's in a galaxy called M87. So raise your hand if you do not know what I mean when I say the designation is M87. If you don't know what that means. Okay. All right. So
We'll keep you in the dark.
we will get back to that. Okay, so astronomy isn't just about stars and galaxies. In our present day life, it's used for navigation, communication, weather, medical technology. They do medical scientific experiments in space, climate science, very important. So without this research, a lot of our modern technology wouldn't exist. You can Google Neil deGrasse Tyson and scientific experiments in space. I've seen him bend the ear off of an interview about all the science that was done in space and what we have today that we use in our everyday life. That was a result of what experiments were done in space. Okay. So a lot of these observatories, when they were originally built, or they still are, when they're built, they're put on mountaintops because at the time that was the best place to put them. You put them high up because you want to get as high up in the atmosphere as you can, because the images are going to be best with the least atmosphere you're looking through. And we even use that as amateur astronomers. So we'll go to a location. If we can get to a 4,000-foot location compared to a 1,500-foot location, we're going to do it because that 1,500 feet or whatever makes a difference in your images that you're viewing through your telescope. So it's this, it's a universal approach, which is get above. That's why we have space-based telescopes. Get above the atmosphere on ground, get as high as you can, because you're looking through less atmosphere and it distorts the image. So you use
ladders with our scope.
What's that? That's why we use ladders with our scope. Get as high as you can. Next.
Just getting out of the small.
Yeah. Yeah. And so you can go through these. These are just quick, different observatories with showing that they're on tops of mountaintops. And then here's that very large array that I was telling you about, where they use like multiple. That's in a smaller scale, but they use multiple radio telescopes. Okay. This is the Los Angeles basin in 1908. So this is from Mount Wilson Observatory. So you can see why, even though, even in 1908, Los Angeles was a large city, but they could build an observatory on the mountaintop there and use it for research. Next, this is it today. So you can see what a mess that is and how it compromises now the science that can be done at that observatory. So light pollution, it's been a subject that I've been involved in since I got started in astronomy. It's really detrimental to the hobby. And I think it's really gonna be the death of visual astronomy, because a lot of astrophotography can cut through some of the light pollution, not all of it, but let's be, the truth is that if you have a CCD camera on a telescope, you can still get images that a visual observer standing next to you is not going to get. So the visual observer has to get to darker skies if they want to get the best images. Okay. So what can you see with an amateur telescope? Well, you can see a lot, as you all know. I'm preaching to the choir here, as they say, but some of you may not. Is there anyone who hasn't looked through a telescope? You've all looked through telescopes? Okay. All right, so you have? Have you? Which one of your five? Okay, so so these are the things that an amateur astronomer can look at with any telescope: planets, double stars, nebulae, emission dark, globular clusters, comets. Somebody just mentioned the comet. You just mentioned the comet. I heard them. You mentioned it. Yeah, we were talking before about the comet. You got a view of it this morning?
I did not.
Oh, okay. I thought you mentioned that you did. Anyway, there's a comet that you can see in the very early morning. Supernova remnants, which is really one of my favorite objects. If you think about what you're looking at a star that exploded thousands of years ago, and you're still seeing the remnants of that. And the reason that I really like those is because that's really the whole kind of life cycle of how systems are formed. So when you have a supernova explosion, it creates stress in space, and gravity takes that and coalesces it, and then the gravity collapses upon itself, and then new stars and new new stars and new planets are formed. So you know how they say we are stardust because the iron in our blood and everything comes from, that's where it comes from. Okay. And then what can you see beyond the Milky Way galaxy? Well, beyond the Milky Way galaxy, you can see galaxies. You can see other galaxies like the Andromeda galaxy, and you can see clusters of galaxies. This is okay, so this is the Andromeda galaxy. This is NGC 7331, and then this is Stephan's quintet. This is 5 galaxies. So you can see, individual galaxies, you can see groups of galaxies, pairs of galaxies, interacting galaxies, face-on galaxies, where you can see the spiral arms, edge-on galaxies, which are really pretty, and that's kind of like a subgenre in the astronomical community. There are people who really focus in on viewing edge-on galaxies. And then one of the most amazing things that you can see as an amateur is, before in our galaxy, within the Milky Way galaxy, we were seeing the remnants of a supernova explosion that happened in our galaxy thousands of years ago. Here, you're looking at a supernova explosion in another galaxy. So you're looking at a star that's in another galaxy, and that is just mind-boggling. All these stars you see in this image are in our galaxy. These are just foreground stars. They're just in the way. This star, though, belongs to this galaxy. That star would have exploded, depending on how far away the galaxy is, thousands, if not millions of years ago. So for example, if we got if we had a supernova explosion in the Andromeda galaxy, and we heard, oh, it just got discovered last night, it's the first night, blah, 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 and you run out and you're looking at it, well, that star exploded 2.5 million years ago. You're just seeing the light from it now. So when you look at these supernova explosions in these galaxies, it's just amazing to think about what you're seeing. You're seeing a star that exploded maybe 20 million years ago in another galaxy, and you can see that with a, it doesn't have to be a very big telescope to do it, okay? So that's what was going on now. So it got me thinking about, well, what were they doing at colonial times with astronomy? Because we know what we do now with it. Well, what were they doing back in the mid 1700s or so? And astronomy for colonial America was used more in a practical sense, because there were no observatories in the United States, in the New World, in the colony. So there were observatories in Europe, in Greenwich and Paris and Switzerland. And as you can see here, the European astronomers were gentlemen, scholars, clerics. They were employed by royal courts, or they were members of some royal society. But in the I keep wanting to say in the United States, in the New World, there were just a few colleges. Harvard, Yale, and Princeton had astronomy programs and professors, but a lot was just private individuals, and there was no government funding. So this was all done either through the college or as an individual. Okay. So interestingly enough, George Washington owned several spyglasses, and he was frequently requesting and purchasing them during the Revolution. He understood the benefits of astronomy, not the way we think of it, not as like, I want to look at that galaxy or that double cluster or something like that, but he understood science. And he knew these spyglasses would give him an advantage as a commander. So even though he wasn't using them to look at the universe, he understood the implications of it. But he also did, and I'll show you this in a second, he also understood the science of astronomy and how it could be used to his advantage as a commander. He also had a Dolan spyglass. We found this in his in a journal of his. So it's I'm not sure I understand what the Shuttleworth of London means, but this Dolan spyglass is a very, very high-end spyglass, a very, very expensive piece of equipment, kind of like the Takahashi of today. I mean, this was not a toy. So this showed, not only did it show Washington's status, but it showed that he was serious about his optics. He wanted the best that was available to him. Okay. So Washington, as I said, he was really locked into astronomy. So here's an example. These are just 3 examples in no particular order. So this is regarding a solar eclipse, and this happened in 1777. So one of Washington's men came to him and said, there's going to be a solar eclipse next week. And they knew this from almanacs. So those who were more educated, who could read, who bought almanacs, who were into science, they would have this information. But not all Washington soldiers would have had this information. They would have been still kind of in the dark ages about what was going on in the night sky. So Washington's soldiers said to him, I think you need to alert the troops to this. So he said, this event, without previous knowledge of it, might affect the minds of the soldiery and be attended with some bad consequences. So basically, he did not want the soldiers freaking out when the solar eclipse happened. So Washington understood this. He knew what a solar eclipse was. So he got to his troops to educate them and let them know it was nothing clear. And if you think about that, I mean, you know, when Columbus came over to America, he used eclipses as a tool of his power. His knowledge of eclipses could be used to intimidate the natives, to think like, okay, you know, my God can take the sun out of the sky if we don't get what we need, you know, blah, blah, blah. So, you know, but that was in the 1400s. This is in the 1700s, and there's still people who are just not educated on what a solar eclipse was. This is one of my favorite ones because Washington records a bright meteor. And so he says, a very remarkable meteor was seen this evening and passed in a direction from northwest to southeast with great velocity. And you can see that, you know, he didn't just say like, wow, I saw a bright object in the sky. It was really cool. I don't know what it was. I mean, he knew what it was. He also recorded the direction of it and tried to estimate the brightness of it the way we would if someone said like, yeah, I'm looking at that supernova. The first thing people ask is, what magnitude is it? How bright is it? How does it compare to something else? So this is kind of like what he was, you know, he was just instinctively locked in on that. And then this is one where he explains why he can't move troops. He says the nights are now too dark for the attempt. So as we all, you know, we have our dark window on our calendars and we lock that in because that's when we're going to observe or not observe. Washington had basically a dark window locked in on his calendar, so he would know when he could move his troops and when he couldn't move his troops. So this is how he used astronomy to get through what his responsibilities were. So astronomy in America focused on calendar making, almanacs, navigation. Poor Richard's almanac was one of the ones that would have been used a lot. And the astronomers in America were mostly clergymen, teachers, and surveyors. Washington was a surveyor. Okay. So this is really important. What's happening now in America is you're getting into the Enlightenment period. And that's where science is starting to overtake, for lack of a better word, pseudoscience. So people are now starting to see that they can, that the world has some order to it. And they want to investigate that order, and they want factual information. They want information that has been tested. So they start moving towards the scientific method. And keep in mind that this is only, I don't know, maybe less than 100 years, but I think even closer to 70 years, if I remember correctly, since the last witch was hung in Salem, Massachusetts. So it's a, that's, you're just talking about a big transition from what people believed or didn't, the lack of knowledge they had about the world around them and what they're seeing now. So in America, this becomes just more, it's just very practical. They're using this for everyday life now. Timekeeping, for agriculture, they're learning how to plant their crops based on the seasons of the year, and they're not necessarily, it's not so specific that they're looking at, say, oh, Leo's rising, I better go out and get my wheat crops planted or something like that. But it would tell them, okay, time to start checking the fields, time to start. It would reinforce to them that the season is changing and it's time to start thinking about what we do in the springtime. Navigation, they used it for, to navigate ships, and it was very important for just practical life, for buying and selling and trading goods. They had to know how to navigate to do it. Land boundaries were done through surveying, which uses stars to, and the altitude of the sun to make your measurements. Calendars, and again, night operations and navigation depended on the moon and the stars. So this change towards this Enlightenment kind of thinking was really crucial to America, and it's really crucial. I believe it. Did anybody see the Ken Burns documentary on the American Revolution? You should if you haven't. It's just fantastic. A lot of this, I mean, once I saw that documentary and had this information that I had researched, I saw how, I think one of the reasons we were so successful against the British was that we just knew how to use this information to our advantage and make it work. So I just copied this slide and reintroduced it because this is from the earlier part of the presentation of the Astronomy Now, to show that what they were doing is basically very close to what we do now. We just do it, we just have way more knowledge and technology, but they were doing it for navigation, communication, weather, well, not necessarily climate science, but you look at the point, they were using this information for the same reasons that we use them now. Okay. These are some of the key figures of the Enlightenment period, were Ben Franklin, John Winthrop. So I mentioned before that Harvard, Yale, and Princeton had astronomy programs. So this John Winthrop was a Harvard professor, and Jefferson, I think, probably, if he hadn't gone into politics, would have just been one of the greatest scientists of our time. I mean, he already is one of them, but he was just an amazing man. So think about that period where you had Washington, Jefferson, and Franklin all kind of their peers. What a time to be if you were living in that period. You've got these minds that are trying to move everything forward scientifically. Okay. And then I stumbled upon, I should say I stumbled upon, because I didn't really know that much about David Rittenhouse. And I know you're a librarian here. Dawn, is that?
Mary?
Mary. Oh, Mary, I'm sorry. Yeah. Emailed me. Oh yeah, you sent me the copy of her email. So she was really all over this, and I really appreciated what you forwarded to me from her about the two different almanacs that were being used, and that's right up there with the Ken Burns documentary about the loyalists versus the patriots. But David Rittenhouse is a really fascinating person. So, okay. So he was born, his birthplace is along the Wissahickon Creek. I actually took this photo. We were going to go out hiking to the Wissahickon Creek anyway, and I knew that someone mentioned to us where his birth house was, so we took a hike over there to see it. But so his father was a farmer, his grandfather was a paper maker, and his great-grandfather established the first paper mill in the British colonies in the 17th century. So if you're ever over in that Wissahickon area, you'll see, I think there's more than one paper mill road, and I never understood that, and now I do, that these are, I'm sure they were named after the Wilhelm Rittenhouse. Okay. David Rittenhouse started out as a farmer, following in his, well, that's what his father needed him to do. They were getting away from the paper mill industry, and he wanted him to be a farmer. David Rittenhouse was not interested in farming at all, not at all. First of all, he was a very slight of build person, and he wasn't interested in a lot of physical activity. And he was very intellectual in nature. And as I said here, he would rather sit around after he was done his farming duties, reading Newton's Principia. Not many people do that as a hobby, but that's where he was extremely intellectual. So he did what he needed to do for a while. Then he became a watchmaker, and his watches were very well constructed, and he wasn't really that interested in making them really flamboyant or attractive. He was more interested in just the precision of the timepiece. He was a surveyor. He was instrumental in determining the Mason-Dixon line, the border between New Jersey and New York. He was a member of the American Philosophical Society that was founded by Ben Franklin. And when Franklin died, David Rittenhouse became the president of the American Philosophical Society. And as we'll see in a minute, because of his international acclaim, he became a fellow of the Royal Society of London, and also of the American Academy of Arts and Sciences in Boston. Okay. So this first bullet here. This is his big turning point in his life. He became world renowned, and that's no exaggeration, world renowned for his successful observation and calculations of the transit of Venus. They had already done some recordings. I think it was 8 years earlier. The two transits come within 8 years apart of one another, and then there's long distances in time before that happens again. And they already had one set of data, and now the whole world was basically excited about this second transit because they wanted to get out and measure it a second time to improve upon what they did the first time. So David Rittenhouse got involved in that. They used 3 locations on the East Coast. So they used Philadelphia, Wissahickon, and Elk Neck, Maryland. They had a telescope down there. But David Rittenhouse built the telescope himself for this transit. Now, this is a transit telescope, so it just moves in altitude. But he ground the lens, built the telescope, and made it. And then he built the timing devices that were needed on it based on his watchmaking experience. So it's quite an incredible a piece of equipment. I believe someone mentioned to me that there might be a replica of that at the Franklin Institute, but not the original. I'm not sure what happened to the original. He constructed an orrery. Does anyone not know what an orrery is? Okay, well, we'll get to it. I'll show it to you. It's really fascinating thing. So
On the wall, on the shelf over there.
oh, okay. Yeah, these are, I mean, they're amazing pieces of science. So he constructed this orrery. He combined his craftsmanship as a clockmaker with his knowledge of astronomy. And Washington was friends with Rittenhouse, and Rittenhouse made a pair of eyeglasses for Washington. So that's just shows you how connected David Rittenhouse was. But it was the transit of Venus that made him world renowned. This is the only piece of math I've ever thrown in anything. I have no idea what this means. I'll just be honest with you right now. But this is how transits are calculated. And this is how smart these guys were back in the mid 1700s, because this is what they were doing to get these calculations to hone in on what they're trying to calculate is the Earth-Sun distance. And after Rittenhouse's contribution to it, they got it almost exact, 93 million miles. It's really amazing. So you skip by that. This is a one image of the orrery. So it's constructed so that the planets move according to their relative speed to one another, and they actually have the moons of Jupiter in there as well, and they move in the exact same motion that they do. So it's kind of like the first app that was ever, it's like Sky Safari before Sky Safari got made. There's another.
Include retrograde?
What's that?
Did it include retrograde?
Yeah, it did. Yeah. So there it is, and you can see it down at it's on the University of Penn's campus. This is something that I was just curious about. So in this biography that I read, David Rittenhouse comments that he observed this comet, and he concluded that the comet was the same one he had seen 10 or 12 years before. And then you can read the rest of that. The thing that was interesting about that is that this comet is called Lexell's Comet. And Lexell discovered this comet, but the comet was a, help me out here, the comet, it just comes and goes. It's not, what's that? Yeah, period. So it's just coming into the solar system and then leaving, never to be seen again. And that's what Lexell commented when he discovered it. That was a periodic comet, it was coming one and done. Yet Rittenhouse says that he was sure it was the same comet that he saw years earlier. And Rittenhouse was so precise with his calculations and his observations and his knowledge that I just found that that contradiction really pretty amazing. So I've been trying to look into that, but I have not really gotten any further information. But it's something I'm just very, very curious about. So there you can see I put here. So I put Sky Safari to Wednesday, June 20th, 1770, 6:34 a.m. That's when David Rittenhouse said he observed the comet, and there it is. So this is a quote attributed to David Rittenhouse. If the enemy should invade this part of the country, as Archimedes was slain while making geometrical figures in the sand, so should I die making a telescope. You can't ask for anything better. And willing to die for his telescope. So, this just really sums up how dedicated he was to science, astronomy. He got involved in politics, also David Rittenhouse did. And I think, a lot of it at the time, that's what people had to, they almost had to get involved. And he had so much clout that he was asked to take that role on. But he was a scientist at heart, and this really sums it up. So now, I mentioned to you about, we said that there was a photograph of a black hole in a galaxy called M87 in the constellation Virgo. And I asked everyone if they knew what the M stood for, and everyone said they did except you. So you've been very patiently waiting, so thank you for that. So I'm going to tell you what the M stands for. So M stands for Messier, okay? And Charles Messier was a French comet hunter. And as you can see here, he's credited with the discovery or co-discovery of 13 comets. Now, when I talked about Lexell's comet, Lexell actually worked with Messier, but Messier didn't always take credit for all of his comet discoveries. He did give some of his co-scientists credit for them. So he gave Lexell credit for the discovery of that comet. But what Messier would do, he really was hyper-focused on discovering comets. So he would go out every night, whenever the moon wasn't up, when it was clear, and he'd start scanning the skies and looking for comets. And he would see something, he wasn't sure if it was a comet, he would focus in on it, he would track it, and find out, no, that's not a comet. So he would record the position of it, because he didn't want to come back to that again another night and say, oh, look, maybe I discovered a comet. He could look at his coordinates and say, no, I saw that last week or whenever. That is not a comet. I can just ignore that. So he started compiling a list. Okay. And this is the list of objects that he compiled that are not comets. And this is the Messier catalog. So basically, what this man was doing was compiling the single most, I don't think it's an understatement to say, maybe the most iconic astronomy catalog. And that wasn't why he did it. He compiled these because he didn't want these. He basically had very little interest in these. He was interested in comets. So it's ironic that hundreds of years later, he's more famous for the things that he threw away than the things that he kept. These are some of the things that colonial astronomers could see. I mean, they had a pretty good, they obviously they could see the planets. They could actually see Uranus. David Rittenhouse did see Uranus. It was discovered in 1781, I believe. He read about Herschel's discovery, and then he wanted to look at it, so he went out and looked at it himself. So they could see the planets, they could see the moons of Jupiter, they could see the moon, they could see the sun. They had solar filters that they could use, and Galileo was even looking at sunspots. So they knew how to do this to to observe these things. So I think, when you think of us as amateur astronomers, what we see now, here they are in the mid 1700s. They've got some pretty good telescopes now. They're not like they're not using what Galileo was using. And now they can start seeing some things. You can skip that one. Okay, so going back again to what we had talked before, they would see these constellations rising, and this would tell them, that seasons were changing. So when Leo is rising, they know spring is coming. When Orion is setting, they know that winter is ending. They would see the summer triangle. There were records of people recording the triangle in the sky. So they were seeing it the same way we see it. That's the first three brightest objects to appear in the summer sky. They would certainly see the Big Dipper, and the Pleiades would be, the rising of the Pleiades would tell them that fall is coming and winter is not far behind. And they would certainly see the Andromeda Galaxy naked eye. They would see the double cluster naked eye, and they probably saw M33 naked eye. They didn't know what they, they had no idea what these were. They had no idea that they were galaxies removed from our galaxy. That didn't happen for a long time. Does anyone want to take a guess as to when it was determined that these galaxies are actually objects that are not in our galaxy?
Over 100 years.
1920, yeah. Not that long ago. I mean, it's not that long ago. That this debate was still going on. So, in the one hand, sometimes science can move real fast and technology can move real fast. And then in other instances like this, it really took a long time for them to figure this out. So this is my favorite astronomical quote. And thank you.
Everybody forgets to post the last panel, that cartoon. It's Calvin responds that all we did was I think it was flip rocks in the stream all day. And
You're right. You're right.
It's like, yeah, I mean other people.
Thank you. Maybe I'll add that in.
Any questions for Rob?
Any questions that I can answer? No. Okay. Well,
Thanks again.
Thank you very much. I appreciate it.
And again, please hang out. Forget to mention, the library is under renovation. So we will have our social hour in here. There's food on the table just outside the door. So grab some, come on back in, hang out. Just stay out of the library. It's a little bit of a mess in there. And again, please, let's make our new members and guests feel welcome. So,
Very good.
all right.
Thank you.